Hello, so this is the last video of chapter 9, and we are going to think about another numerical example. It is about COVID-19 vaccine. Well, by the way, I got this vaccine last week. Okay, anyhow, suppose that I believe that uh, you developed a new COVID vaccine, and you believe that your new vaccine works like with probability 90%. So those who got this vaccine uh, would have antibodies with probably 80% of those who got this vaccine would have antibodies. That's your like hypothesis, right, for a certain vaccine. So then you can set up the hypothesis like this. P is the probability of developing antibodies after vaccination, right? So that is 80% you believe. Of course, the alternative is different from 80%. Now, this is a special example because whether you have antibodies is a binary variable. You have it or not, right? So it is yes or no type binary variable. So we are going to define the underlying random variable in this way. X is a random variable, so it takes 1 if you have antibodies, 0 otherwise, right? So the parameter of that we are interested in is the success probability of this binary variable, which equals the mean by a property of the binary distribution, right? You may remember. So we are interested in the probability, but you may interpret that as a mean. That equals the mean. So we can apply the hypothesis testing method for the mean. That's how we justify our application. Still, there is one thing you have to remember, that is, due to the binary distribution structure, the standard deviation of x should follow this formula. Okay? So remember, the variance for a binary variable was p times 1 minus p. Success probability times failure probability. So its standard deviation must be square root of the variance. Okay? Just remember to use the standard deviation. Okay, then one more thing. Like our hypothesis testing assumes the null hypothesis until it is rejected. So we calculate everything based on the assumption that your hypothesis is correct. So in this scenario, in this example, we assume that P, the probability of antibodies, is 80%. We have to maintain that assumption until it is rejected. Therefore, the standard deviation is also implied by the hypothesis, right? If the hypothesis is true, the mean is 0.8, but at the same time, but also the standard deviation should be calculated like this. So your standard deviation is already given by the null hypothesis, 0.4. So we have to use this standard deviation wherever you need the standard deviation. Okay? So in the previous example, the standard deviation was calculated from the data, but not anymore. We don't need data to calculate the standard deviation. Okay? This is an important point, and if you follow the process we learned, then it is pretty natural. Okay? Then this standard deviation will be used here. Like if your null hypothesis is correct, then the sample average will follow approximately a normal distribution with the mean that is assumed in your hypothesis with a standard error that is also implied by your null hypothesis. In our earlier examples, this part, the standard error, the variance part, was not fixed by the hypothesis, but now it is. Okay, so the parameters are given by 0.8 and 0.4 divided by the sample size. Okay, now, but remember, like at this moment, I did not give you any data. I did not tell you anything about the sample, right? Just only based on the sample size, only based on the null hypothesis, we get this sampling distribution except for the sample size. It only remains to plug in how many observations you have. Okay, then you get the null distribution, the distribution of X bar under the null hypothesis. Okay, that's something different, something new in the hypothesis testing from the other statistics theory. Now I tell you the data. You have 100 observations and you found 100 people, randomly chosen people who got the vaccine, and only 75 of them had antibodies. In this case, what is the p-value? To calculate the p-value, you have to calculate the t-statistic first, and then you calculate the tail probabilities outside the t-statistic. So try it by yourself. It's an important exercise. Okay, let me start with t-statistic. So first, your data. From your data, out of 100, you get 75. So the probability of success is 0.75, which equals the sample average too, right? So sample average X bar is 0.75, because, right? The mean equals the probability. And the hypothesis is 0.8. You believe that the probability should be 80%, so there is a 5% point difference. You have to standardize the difference by the standard error. Standard error is calculated by the standard deviation divided by square root of sample size. Sample size is 100. This is simple. And remember, standard deviation was calculated from the formula and the null hypothesis. So it was 0.4. It has nothing to do with the data, 0.75. So you have all the numbers and you get minus 1.25 for the t-statistic. And then now you have to cut the p-value is the value outside plus minus 1.25 on the standard normal distribution. That is easy if you use Excel or a calculator. So calculate this tail probability, and the other tail probability must be the same. So basically these two probabilities must be the same tail probability. So you will get 21.13%. That is the p-value. Okay, you calculate the p-value like this, and remember the point was standard deviation is specially fixed by the null hypothesis. Anyhow, so after calculating the p-value, you have to decide whether to reject the null or not. So under what significance level can you reject the null hypothesis? Okay, so remember the p-value is the ranking of suspiciousness. It's from its top 21%, right? Our observation, our data is suspicious in the ranking. It's 21% from the top. So 21% is greater than, it's outside of 1, 5, 10%. So no matter what you choose among these three, you are not rejecting the null hypothesis. P-value is always greater than the significance level in any of those candidates, right? So the answer is none, right? E is the answer. Next, we take the critical value approach. And your practice, your turn. Try this at 5%. Okay, so pause the video if you need more time. So first, critical values are centered around your hypothesis, which is 80%. And all of the choices have centered at 80%, that's correct. And you allow margin around 80%. That is, the margin depends on the 5%. So at 5%, you have to use constant 1.96. 1.96 is the approximate number for 5% tail probability. Then you apply the formula like this. So the center is 0.8 hypothesis, and 1 point, z alpha over 2 is 1.96. And this is standard error we calculated earlier. Again, the standard deviation must be calculated following the formula and the hypothesis, right? So then you know all the numbers, just do the simple algebra. You will get 87.84% down to 72.16%. So even though you believe it should be 80%, but you have to allow margin wider than that. And then, remember, in your data, you get 75% antibodies. Can you reject your null hypothesis? Okay, so like these critical values imply that any data that have the sample mean in between these 2 points will be accepted. It's considered consistent with your null hypothesis. So you get 75%, which is above the lower critical value. So it is within the margin. So you don't reject the null hypothesis because the sample average is close enough to your null hypothesis. So you cannot reject the null hypothesis. That is the answer. Okay. Like last page, this is the last page. So you for comparison, like in the confidence level, like in the confidence interval chapter, we used very similar formula, but at that time the standard deviation was calculated from the data, right? So the margin is different. If you calculate the confidence interval from this data of 75% antibodies, then your standard deviation must follow the data point 75%. But now we use standard deviation that follows 80%, right? So like it also illustrates the different approaches for confidence interval and hypothesis testing. The formulas are pretty similar, but the underlying philosophies are pretty different. But it's pretty clear. This illustration clearly shows how they are different. Okay, thank you for watching. This is the end of chapter 9. And chapter 10 is actually a continuation of hypothesis testing. We are going to learn additional issues, more topics related to hypothesis testing. Okay, see you there. Bye.